Math 1314, section IC1, spring 2022, Tyler Junior College. Homework 9.3/9.4, logarithms and their properties. Video 6, properties of logarithms. Now, we've kind of already summarized these in previous videos as we stumbled across them. I'd like to try to summarize as many as I can and bring in some that we haven't seen before that we'll use in the next video. Now, these are in no particular order. They're just the order that pop into my head. Well, one property that we already saw in the previous video was when we had a log whose argument was 1. Now, the base could be anything. What question is this asking? This is asking what power turns b into 1? What power will turn any base into 1? 0. And just like that, there's property number 1. Now, most of these properties have what I call a checking statement. In other words, the reason why the answer is 0. The reason the answer is 0 here is because b to the 0 power is equal to 1. And I'm going to type the caret symbol for exponent so that I don't have to stop and draw a 0 or type a small 0 and put it in the right place. How about this one? What happens if we take log base b of b? And by the way, for all of these, I should mention that all of these have a valid base. So we're going to preface this by saying, for any base b greater than 0 and b not equal to 1. I have to go grab a not equal sign from Microsoft Word. Give me 1 second here. Okay. All right. So for any base b greater than 0, b is not equal to 1. Number 1, log base b of 1 is equal to 0 because b to the 0 power is 1. What about number 2, log base b of b? Well, what question is this asking? Every log asks the same question. What power turns the base into the argument? They both are b here. What power would you put on b to turn it into b? Well, the only power that keeps something the same is the first power. So that didn't take too long. Log base b of b is equal to 1. And that's because, I guess we're back up the font size. You know what? We'll keep it 36-point font. Don't really care. It's probably easier to read, so we'll leave it there. Put that one in. Okay. Okay, because b to the first power is equal to b, which is trivial. Anything the first power is itself. But there was a third one that we had. The third one that we had looks something like this. If you have a logarithm base b, but your argument was b to some power, and I believe we said b to the nth power. The question this one is asking is what power would turn b into b to the nth power? What power would you put on b to turn it into b to the nth power? Well, isn't the power I need to turn b into b to the nth power n? That's borderline trivial if you ask the question correctly. Log base b of b to the nth power is n because, and again, this statement is almost trivial when you type it, n is the power that you put on b to get b to the nth power. Duh, anything's equal to itself. That's a reflexive property of equality. Excuse me. Let's see what other ones we can create. How about this one? Number 4. What if you have a log, any valid base, so positive but not 1, and your argument is 1 over that base to a power? Let's think about this for a second. This is asking what power would I put on the base b to get 1 over b to the nth power? Well, what exponent rule creates reciprocals? The negative exponent rule. B to the negative n power is 1 over b to the n power, which means that logarithm is equal to negative n. In fact, this statement that verifies it is sitting over here in red. So let's just slide it over a little bit. And it's under my face right there. You know what? We'll just have to turn my face off right now. And we will type the word because in here. So log base b of log base b of 1 over b to the nth power is negative n, because b to the negative n power is equal to 1 over b to the n. Okay, I want to throw one more out here that we haven't seen before, and I think it's going to show up later. But it goes something like this. Let's say, and I'm going to bring my picture back up. I just think the audio is better when you have some facial expressions. Let's say you take any base b, positive but not 1, and you raise it to the log base b of n power. Now this one seems really weird and out of nowhere, but let's think about it for a second. See the part I highlighted in yellow, log base b of n? I don't know what its answer is, but I know what its answer does. The answer to that highlighted log is the power, and I'm gonna draw an arrow because this is kind of important here. Whatever the answer that is, it is the power that turns the base, which is b, into the argument, which is n. But by definition, and I'm not sure if that yellow is easy to read, so we'll put it in pink. Whatever the answer to that logarithm is, it's the power that turns b into n. I don't know what it is, but I know what it does. As a power, it turns b into n. Oh, wait a minute. It's a power on a b. So what does this thing do? As a power, it turns b into n. It's power. It's on the b. By its own design, it turns it into n. The answer to b to the log base b of n power is n. And that one seems really, that one's a tricky one to wrap your mind around, because it's not just log of what equals what. But number one, it really focuses on what the answer to a logarithm does, as opposed to what the answer to a logarithm is. That yellow thing's answer as a power turns b into n. Well, it's a power on a b, so it's by own design, it turns it into an n. But the other reason I wanted to bring it up is because number 5, coupled with number 3, verify that logarithms and exponential functions are inverses. Don't dwell too much on that, but it does. All right, what other log properties can we bring up here? I felt like there's one missing before we hit what I call the big 3. Let me just look them over again. Base is 1, base is b, base is a power of b, base is a reciprocal of a power of b. I guess we can make one for radicals. Oops. Let me move all this up. So I did not grab the pink statement, but that's okay. Just do that and move it over. Turn my picture off for now. All right. So what is this last, well, excuse me, what is this next one I want to show you? Well, what if we have a log base b, but our argument is the y-th root of b to the x power? Actually, let's take off the x for a second. What if it's just the y-th root of x? Well, the question is, what power would turn b into the y-th root of b? Well, that would be the 1 over y power. That's what fractional powers do. Log base b of the y-th root of b is 1 over y. Let's put that in a red box. Oh, come back. Put this in a red box. And I owe it to the problem to at least type because. And let's move all this over some because it's kind of running into everything. Okay, so now that I've done that one, let's go ahead and put that x power back on the b, which means our numerator would be x. And over here in the checking statement, we would have x over y is equal to the y through to b to the x. So that one, if you know your exponent rule, it's pretty easy to flush out. All right, I got 3 more I want to show you. I was debating on us figuring these out, but for the sake of time, I'm just going to tell you what they are. All right, number 6. We've already written 6. Number 7. Now this one actually has a name. This one is called the product rule. And it goes something like this. Let's say you have a logarithm. Black, please. Let's say you have a logarithm, any base of a product, meaning a multiplication problem. I'm going to write this product as capital M times capital N. Why? Why not? If you have a log of a product, you can split it into the sum of 2 logs, same base, and each factor gets its own log. This could be written in words. You could write it this way. The log of a product equals the sum of the logs of the factors. Factor by definition is part of a multiplication problem. So as I read it from left to right, watch the parts that I highlight with this vanishing pen. The log of a product equals the sum of the logs of the factors. Remember, factor is part of a multiplication problem. So it's almost like a distributive property. You're almost distributing the log across the product, but it doesn't turn into a product of logs, it turns into a sum of logs. Now, there's a corresponding rule called the quotient rule. And you could probably figure out what it is if you remember that a quotient is the answer to a multiplication problem. Give me 1 second to move the product rule up some. I think I grabbed it all. I did, look at me. So that I can move the quotient rule up and have some room for it. And maybe we should draw a line separating the two. Yeah, there we go. All right, so what's the quotient rule? Well, the product rule says if you take the log of a multiplication problem, you get a sum of logs. So what do you think the quotient rule says? Quotient rule says if you take the log any base of a division problem, so we'll say m over n, then you can split it not into the sum, but to the difference of 2 logs, each with the same base. And it's the numerator's log minus the denominator's log. So log base b of m over n equals log base b of m minus log base b of n. Now this one's a little trickier to write in words. It's not impossible, but it would go something like this. The log of a quotient, i.e. fraction, equals the log of the, we'll just say numerator. I was going to say dividend minus the log of the denominator. Now, there's a lot of words to say, but this is one of the reasons we use symbols, so we don't have to say all these words. It is worth pointing out that these rules go in both directions, meaning, for example, on number 7, if you see something like this, you can rewrite it like that. And vice versa, if you see the sum of 2 logs, you can condense them into a single log by taking the product of their arguments, and vice versa for the quotient rule. See the log of a fraction, you can split it into the difference of two logs. Or if you see the difference of two logs, you can condense it into the log of a fraction. We will be practicing these things in the next video. One more property. It's called the power rule. If I can get it to draw. 9, please. Thank you. Again, this is called the power rule. And before I give you the power rule, quick warning. In calculus, you have rules called the power rule, the product rule, and the quotient rule. Where'd the product go? For some reason, the product rule, the name of the product rule disappeared up here. Not sure how that happened. We'll just put it back up there. But in calculus, you have 3 rules that are called the product rule, the quotient rule, and the power rule. And unfortunately, they're very different than these. So I should really give these their full names, which is the product rule for logarithms, the quotient rule for logarithms, and the power rule for logarithms. In calculus, you will have the product rule, quotient rule, and power rules for derivatives, but that's a calculus thing. So what is it here in pre-calculus with logarithms? It says this: if you have a log, any base b, of some argument, we'll say m to the p power, p for power. Now be careful. This is not the same setup as rule 3. Do you see the difference between the setup for rule 3, besides the letters being used, and the power rule? It's subtle, but super important. In rule 3, the base of the logarithm and the base of the argument are the same. Those two things matched. These two b's matched. But in the setup for the power rule, we don't necessarily have matching bases. In other words, the base of the logarithm, which is represented with a b here, is not necessarily the same as the base of the argument, which we're representing with a capital N. So we can't just say the answer is p. Just like back here on number 3, we said the answer is n. What we can do, however, is this. We can take this power and move it down in front of the logarithm as a factor, p times log base b of m. Now, just like the product rule and the quotient rule, this is reversible, meaning this is saying 2 things. If you have a log of an argument and there's a power on the argument, then you can pull the power off the argument and put it in front of the log. Or in reverse, if you have a log with a coefficient in front, a number in front of the log, then you can move it up. You can move that coefficient up into the logarithm as a power on the logarithm's argument. I call these last 3 rules bidirectional because from one direction they do one thing, but in reverse they do the other. So that's all the power rule says. It says if you take a log of something with the power, you may pull the power off and put it in front of the log. Or in reverse, if you've got a number in front of a log, you can move it inside as a power. Now, this is a very, pardon the pun, powerful rule for 2 reasons. Number 1, it's the only rule where we are permitted to take something inside the logarithm and move it outside. And number 2, it is the only rule that you've ever seen until you get to calculus where you can take something that's in the exponent and bring it down to the ground with everybody else. So it's got an inside-outside flavor to it and a top-to-bottom flavor to it. I'm in the exponent, I'm on the ground. I'm in the exponent, I'm on the ground. So those 2 things are going to be things that we're going to use a lot when we get to the next homework. Now, as far as this homework goes, we only really have one more video to go.